Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Khairum Hamzah. Today, I want to present my research with a title, Multiple Cracks Problems in Bonded Dissimilar Materials, supervised by Associate Professor Dr. Nik Muhammad Asri bin Nik Long and co-supervisor, Associate Professor Dr. Nur Razak bin Senu and Associate Professor Dr. Zainuddin Eskavatov. My presentations today consist of 5 items. The first one, introduction, literature review, methodology, numerical result and discussion. Last but not least is conclusion. For the introductions, fracture mechanics is very important in the field of engineering that been discussed by researchers in recent decades. One of the sub-area in fracture mechanics is crack problems that play an important role on the effectors of the strength and toughness of the engineering structure. In order to identify the stability behavior of the material containing cracks, can be obtained by calculating the value of a stress intensity factor. Cracks problems usually come out with two situations. The first one, a crack without thermal, and the second one, crack with thermal. And then the crack can exist in terms of a single crack and multiple crack. And then for the types of materials, generally it are four, which is infinite plane, finite plane, half planes, and bonded dissimilar material. My research focus on the case of bonded dissimilar materials and for the case of without thermal crack. The main objective of this research is to formulate a new system of hypersingular for a crack in the upper parts of bonded dissimilar materials, to formulate a system of hypersingular integral equation for two cracks in the upper parts of bonded dissimilar materials, and then we analyze the behavior of stress intensity factor for different crack configuration, position, and elastic constant ratio. For the literature review, we are using a complex verbal function introduced by Mushkilishvili 1953 because this function is the simplest and most rigorous method. In order to solve this function, we need a counterpart method such as hypersingular, singular, or freedom integral equation. A number of papers have been published to analyze the stability and safety of materials by calculated stress intensity factor, such as for the case of infinite plane, finite plane, and half plane. For the case of bonded dissimilar materials, Chain 1986 used a freedom integral equation in order to solve multiple inclined cracks problems in bonded dissimilar materials. Chen and Hasabi 1992 used a logarithmic singular kernel for the case of a circular arc crack in the upper parts of bonded dissimilar material. Zoll et al. 2008 used a complex Cauchy-type singular integral equation for the case on an arbitrary cracks problems. Berman 2018 used randomly oriented inclusions for the case of H semi-infinite interface and substrate crack in bonded dissimilar materials. Methodology, a complex verbal function method introduced by Mushkilishvili 1953, involved in terms of stress component, resultant force, and displacement as given by these four equations, whereby G is the shear modulus, kappa represent for the plane stress and plane strain, whereby V is the Poisson ratio. If we differentiate equation 2, we can get equation 5 in terms of normal and tangential component. According to Netlong and Eshkawatov 2009, the complex potential function for the case of infinite plane can be represented by equation 6 and 7, whereby gt is the crack opening displacement function as equation 8. In order to find a complex variable function for the case of bonded dissimilar materials, we need to use modified complex potential function for the crack at the upper part consists of principal and complementary part as equation 9, whereby the principal part is also equal to the complex potential for the case of infinite materials, and then crack in the lower plane represented by phi 2 and psi 2. So we need to find what is the complementary part in order to solve the crack in the bonded dissimilar materials. By using the continuity conditions of the resultant force and displacement function, like equation 10 and 11, we solve these two equations, we can get the complementary part as equation 12 until 15, whereby gamma 1 and gamma 2 are represented by equation 16. In order to find the hypersingular integral equations for a crack in the upper parts of bonded dissimilar materials, we need to define two traction components in terms of principal and complementary parts, and then we can get as equation 17. And then for the case of two crack in the upper parts of bonded dissimilar materials like this figure, so we need to define four traction component in terms of principal and complementary part. After using the mathematical formulations, then we can get crack L1 at the upper parts of bonded dissimilar material as equation 18, and then crack L2 at the upper parts of bonded dissimilar material like equation 19. If we set G2 equal to 0, our equations reduce for the case of half plane. If we set G1 equal to G2, our equation reduce for the case of infinite plane. In order to find the numerical method, we use the quadrature formula as equation 20, 21, and 22. And then for the numerical result and discussions, in order to find stress intensity factor, we use equation 23 and 24 to find the non-dimensional stress intensity factor at the crack tips. For the case of an inclined crack in the upper parts of bonded dissimilar materials, we can get the numerical result as a table 1, and then we compare with Isida and Noguchi 1993. From this table, we can see that our result is agree with those of Isedane and Noguchi 1993. F1 at crack tip A1 is equal to F1 at crack tip A2, and F2 at crack tip A1 is equal to the negative F2 at crack tip A2. And then for the net case, at the crack tip A1, the strength of the material decreases as alpha increases, and the strength increases as G2 over G1 increases. At crack tip A2, the strength of material decreases as alpha increases, and the strength is increases as G2 over G1 increases. For the case of two inclined crack in parallel in the upper parts of bonded dissimilar materials, and then we can see that our result at crack tip A1, the strength of the materials decreases as alpha 1 equal to alpha 2 increases, and the strength increases as G2 over G1 increases. At crack tip A2, from the result, we can see that the strength of the material decreases as alpha 1 equal to alpha 2 increases and increases as G2 over G1 increases, whereby at graph tip B1, the strength of the material decreases as alpha 1 equal to alpha 2 increases and increases as G2 over G1 increases. At graph tip B2, we can see that the strength of the material decreases as alpha 1 equal to alpha 2 increases and increases as G2 over G1 increases. As a conclusion, the modified complex variable function method were used to formulate the new system of hypersingular integral equation for the crack problems in bonded dissimilar materials with different elastic constant, which is G1 and G2. And if we set G2 equal to 0, our system reduced to the half plane. And if we set G2 equal to G1, our system reduced to the infinite plane. The value of non-dimensional stress intensity factor for crack in bonded dissimilar materials depend to the elastic constant ratio, the position of the crack, and the distance between a crack and the boundary. This is our references, and then thank you.